Cross-validation based model selection is a video provided for Stanford Crowdsource Initiative, and my name is Ophelia. In the last module, we covered some validation methods for working with regression models, but it seems they do not produce very encouraging results, and we can read between lines. We can imagine an algorithmic way to help us. The most expensive methods are less so. We return to face the border of an optimization problem. In this new chapter, we will try to approach this algorithmic way. We're trying to decide which algorithm to use. We train all the applicable models and make this table, collecting data. Suppose we train 6 models, and each provides a measure of train error determined. However, each of them we apply tenfold cross-validation error. We find more consistent error. According to this measure, we chosen model wall F3. Here are several questions to answer. We use LOOCB for k nearest neighbor and not tenfold cross-validation. The reason is poorly computational. Cost of time computing. For k and n and other non-parametric methods, LOOCB happens to be as cheap as regular predictions. Second question. Why stop at k equal to 6? No good reasons, except it looked like things were getting worse as k was increasing. Third question. Andrew Ang-like question. Are we guaranteed that the local optimum of k versus LOOCB will be the global optimum? No, in fact, the relationship can be very bumpy. And fourth question. What shall we do if we are depressed at the expense of doing LOOCB for k equal to 1 through 1000? Idea 1. K equal 1, k equal 2, k equal 4, 8, 16, 32, 64 until k equal 1024. Idea 2. Hill climbing for an initial guess at k. We can see 5 questions. Among the 5 questions above, the third, fourth, and fifth involve choosing the value of a real value parameter. What shall we do? Idea 1. Consider a discrete set of values. Often best to consider a set of values with exponentially increasing gaps, as in the KNN example. Idea 2. Compute the derivative of LOOCB respect to the parameter and then do gradient descent. Third question. to consider the scale factors of non-parametric distance metrics. However, we must ask the question of what other bizarre alternatives we have to cross-validation based model selection. 1. Cross-validation. 2. Archaic information criterion. 3rd. Bayesian information criterion. And 4th. Structural risk minimized with VC dimension. And keep in mind that AIC, BIC, and SRM advantage, we only need the training error. Cross-validation errors might have more variance. SRM-VC is wildly conservative. Asymptotically AIC and leaving out cross-validation shall be the same. Asymptotically BIC and carefully chosen k-fold shall be the same. You want BIC is you want the best structure instead of the best predictor. AG for clustering of Bayes net structure finding. Many alternatives, including proper Bayesian approaches. AIC, Archaic Information Criterion, is a measure of the relative quality of a statistical model for a given set of data. Given a collection of models of the data, AIC estimates the quality of each model relative to each of other models. Hence, AIC provides a means for model selection. AIC is founded on information theory. It offers a relative estimate of the information lost when a given model is used to represent the process that generates the data. In doing so, it deals with the trade-off between the goodness of fit of the model and the complexity of the model. AIC does not provide a test of a model in the sense of testing a null hypothesis, i.e., AIC can tell nothing about the quality of the model in an absolute sense. If all the candidate models fit poorly, AIC would not give any warning of that process. Bayesian information criterion. In statistics, the Bayesian information criterion is a criterion for model selection among a finite set of models. The model with the lowest BIC is preferred. It is based in part in the likelihood function and is closely related to the archaic information criterion Prioritization. When fitting models, it's possible to increase the likelihood by adding parameters, but doing so may result in overfitting. Both BIC and AIC resolve this problem by introducing a penalty term for the number of parameters in the model. The penalty term is larger in BIC than in AIC. Structural risk minimization is an inductive principle of use in machine learning. Commonly, in machine learning, a generalized model must be selected from a finite dataset with the consequent problem of overfitting. The model becoming too strongly tailored to the particularities of the training set chosen and generalizing poorly the new data. The SRM principle address this problem by balancing the model's complexity against its success as fitting the training data. Many alternatives, including proper Bayesian approaches, models, and non-models. All note it is altered an emotional problem. Overfitting, what can be done about it? First, hold out an additional test before doing any model selection. Check the best model performs well even on additional test set or randomization testing. In this module, we have covered the selection between different models based on different criteria, from the simplest to those based on information theory are actualizing raising more questions than solutions. Goodbye, see you.